Hello everyone, this is fifth lecture of week 11. Recall that we were learning about Karmakar's method in the past few lectures, right. So, we learnt the procedure completely, and we have also now worked out an example, right. So, in this lecture we will work out the so called pathological example that we had actually discussed in the simplex case, right. So, if you recall the simplex algorithm, right, we had actually mentioned about one of the problems where if value of n increases, the number of steps in simplex method is 2 power n, right. So, let us see that example once, right. So, yeah, if you recall the example, right. So, yeah, I think must be little before. So, this was the example if you could recall, right. So, yeah, this was one of the issues that were pointed out in the simplex method, right. So, we are maximizing this particular quantity 2 power n minus 1 x 1 plus 2 power n minus 1 n minus 2 x 2 plus dot 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 plus 2 x n minus 1 plus x n subject to n conditions as well, x 1 less than or equal to 5, 4 x 1 plus x 2 less than or equal to 25, 8 x 1 plus 4 x 2 plus x 3 less than or equal to 125 dot dot dot, yeah, this condition 2 power n x 1 plus 2 power n minus 1 x 2 plus dot 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 plus 4 x n minus 1 plus x n less than or equal to 5 power n x greater I mean all x 1 to x n greater than or equal to 0, right. So, this took 2 power n steps in simplex method, and we have actually come to Karmakar's method saying that it is much faster than simplex method, right. So, at least in the pathological cases, right. So, I mean it would be good if we can work out this pathological case and show that, yeah, I mean we are actually not I mean performing really bad as we are performing in simplex method, right. So, let us check I mean let us take up the same problem, okay. So, I will write down this problem. So, the problem is this: max of 2 power, so I will write m, okay, for a reason. So, instead of n I am writing m here, okay. So, 2 power m minus 1 x 1 plus 2 power m minus 2 x 2 plus dot 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 plus 2 x m minus 1 plus x m. So, this is what you are maximizing and it is subject to m conditions again. So, it is x 1 less than or equal to 5 and 4 x 1 plus x 2 less than or equal to 25, 8 x 1 plus x 2 sorry 4 x 2 plus x 3 less than or equal to 125 dot dot dot, and the final one will be, yeah, more constraints, and the final constraint is this 2 power m x m plus x 1 plus 2 power m minus 1 x 2 plus dot 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 plus 4 x m minus 1 plus x m less than or equal to 5 power n and x greater than or equal to 0, right. So, this is the problem that we are going to solve, right. So, we will first write this in the standard form as we did in the affine scaling method, right. So, first so since there are m constraints, all of them inequality constraints. So, we should have m more slack variables. So, you will have a to be the following, it will be 1, yeah. So, you have many zeros, okay, m zeros to be very precise, right, because there is x 1 to x m, and here you will okay, this one will fill up later. So, this will be 4 1 okay, 0 and 0. So, this will be 8 4 1 and all zeros, right. So, this goes up to 2 power m, 2 power m minus 1, 2 power m minus 2 dot dot dot, and finally, it will be 1, okay. So, these are the constraints, and here you will have identity, right. So, it is 1 0 fine, yeah, I think these can be filled up. Okay. So, yes, so this, and you have x1 to x2m, right. So, yeah, for each of them you have added a slack variable. So, you have 2m variables now, okay. And here you have 5, 25, 125 dot 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 5 power n, okay, and x greater than or equal to 0, right. So, okay, I should have written the minimum in the top, okay. So, I will write that. So, this is minimum of minus 2 power m minus 1 x 1 minus 2 power m minus 2 x 2 minus dot 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 minus 2 x m minus 1 minus 1, sorry, minus x m, okay. And if you want, you can write plus 0 x m plus 1 plus dot 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 plus 0 x 2 m, okay, because you have 2 m variables. So, this is the standard form, okay. So, I now have to convert this to the canonical form, right. So, where you actually add a row with all zeros and a 1 below, right. So, that is one thing that you do. You also add one more variable and call it as 1, right. So, and the b on the right side, right. So, that becomes minus b within the A matrix, right. So, I mean that is something that we have worked out in the previous example as well, right. So, yeah, the 0 1 here, this part has become 0 minus 1 in this place, right. So, you will have this B matrix on the right coming in, okay. So, yeah, so the standard form becomes like this: min minus 2 power m minus 1 x 1 minus dot 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 minus 2 x m minus 1 minus x m plus 0 x m plus 1 dot 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 plus 0 x 2 m, right. So, and here you have a slightly different matrix, right. So, this is 1 0 dot 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 0 1 0 dot 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 0, and here you have minus 5, you have 4 1 dot 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 0 0 1 dot 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 0, this is minus 25, go ahead. This will be 2 power m 2 power m minus 1 dot 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 this is 1, and this will be 0 0 and 1 minus 5 power n, and this is going to be 0 0 yeah, all zeros, and you still have a 1 at the end, okay. So, this is the A matrix, and here you will have x 1 x 2 dot 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 x 2 m and x 2 m plus 1, right, that is equal to 1, right. So, here everything is 0 except the last one where it is actually equal to 1, okay. So, this is and yeah, you have x greater than or equal to 0 for all 2 m plus 1. So, x 1 greater than or equal to 0, x 2 greater than or equal to 0 dot 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 x 2 m plus 1 greater than or equal to 0. So, I will also change this as 0 x 2 m plus 1 because that is also there, okay. So, this is the final problem that we are going to solve, okay. So, I am going to write this matrix for a general value of m, okay. So, that means I will change the values of m and show how many iterations it takes for in Karmaker's algorithm when you just implement this particular problem, okay. So, let us go ahead to the implementation part, right. So, yeah, this was the algorithm that we implemented in Karmaker's method for some other problem, right. So, yeah, the later part we are going to copy it down, okay. But since we are actually going to write down the matrix A, C, X, everything for general values of m, okay. So, that will take a little bit of time, okay. We will do that, yeah. So, I will write down the text, which is Karmaker's method for a pathological case, pathological example maybe, okay. So, it is actually a pathological example for simplex setting, but nevertheless it is a pathological example everywhere, right. So, fine, yeah, okay. So, yeah, we will first initialize m equal to 3, which is the simplest, which is a very simple case, right. simplest case is m equal to 1, but yeah, we will start with this. Okay. Now, I am going to rewrite a, c and x. Okay. Everything else is going to be the same. Okay. I mean the rest of the code is going to be the same. So, yeah, let us write it for a general value of m, right. So, let us initialize c to be an array of zeros, right. So, I can write it as np of zeros of 2m plus 1, right. So, I mean x and c, if you can recall, they have m plus 1, so you have x1 x2 dot x2 m plus 1, right. So, since it is c transpose x, so both c and x will have 2m plus 1, right. So, I will first initialize c to be I mean 2m plus 1 zeros and x to be 2m plus 1 ones. Okay. And yeah, so for a I will initialize it to be zeros of, so the size is m plus 1 into 2m plus 1, right. So, you have I mean you can see that you have m plus 1 rows, right, and the m rows and the last one row. So, it is m plus 1 and the number of columns is 2m plus 1, right. So, I have initialized the sizes, right. Now, I will yeah, change the values accordingly, right. So, yeah, so for C, please note that x1 to xm has some values, but after that it is zeros, right. So, I do not have to change. So, please note this. So, I have got A matrix is fine. So, your C matrix is this minus 2 power m minus 1 minus 2 power m minus 2 minus 2 power m minus 3 dot 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 minus 2 minus 1 and then you have zeros, right. So, this is m plus 1 zeros. So, and this is m value. So, this m plus 1 zeros can be left out as such and I will just code for the others, right. So, you can see that C of 0 is minus 2 power m minus 1 and C of 1 is minus 2 power m minus 2 and so on up to C of m minus 1 is minus 2 power 0, right. So, I will write this as C of I equals minus 1 into 2 power m minus m plus sorry m minus 1 minus I. Okay. So, that if I is 0 it is 2 power m minus 1, if I is 1 it is m minus 2 and when it is m minus 1 it is 2 power 0. Okay. So, that is basically it. So, for xi, okay, so we have to choose an interior point, right. So, I think we did that a little while ago for a fine scaling method. Let us check if we have it as such. Yeah, we have it. So, if you recall, we initialized it, I mean initialized x1 to xm to be 1, okay, and the remaining ones in such a way that Ax is equal to b, right. So, here we will have to do it in such a way that Ax is equal to 0, right. So, again x, so this is x0, okay. So, I said we will have ones for the first m values, right. So, this is m ones, right. So, we need not disturb this, we have ones anyway, right. And so, this one is 4 because 1 plus 4 minus 5 is 0, okay. See the first row. So, you have 1 and you have 4 minus 5 is 0. So, in the next row I am writing this as 20 because 4 plus 1 is 5, 5 plus 20 is 25, 25 minus 25 is 0, okay. And the next one is it will be 8, 4 and 1, right. So, 8 plus 4 plus 1 is 13. So, 13 you have to add 112. So, you have 13 plus 112 is 125 minus 125 will give you 0, okay. So, yeah, that is how you are going to write, okay, and the last one is 1. But now, I mean, yeah, so if it is for particular values of m, I can find out what these values are, right. So, but how do I write it in general, right. So, that is one question that we need to address, okay. So, I mean I will leave this as an exercise, but I mean you can be convinced that the numbers are actually the following, okay. So, it is 5 power. So, yeah. So, yeah, I will write this as m minus I. Okay. So, 5 power m minus I plus 1 minus 2 power m minus I plus 1 plus 3. Okay. So, that is, oh, I have to write I minus m then. Yep. It is I minus m plus 1, and this is also I minus m plus 1. Okay. So, let us check for certain values. So, I claim that for x of I it is this when I is m plus 1 up to 2m minus 1. Okay. For 2m it is 1. So, we can leave that. So, yeah, let us check this for certain values of m. Okay. So, what is x of m? X of m is 5 power 1, that is 5, minus 2 power 2, which is 4, and plus 3, right. So, it is 5 minus 4 plus 3 is 1 plus 3, it is 4, right. So, that is correct, it is 4. And what is x of m plus 1? It is 25 minus 8 plus 3, which is 20, right. And what is x of m plus 2? It is 125 minus 16 plus 3. Okay. So, you have 128 minus 16 is 112. Okay. And x of m plus 3 is 625 minus 32 plus 3, right. So, you will have 628, and yes, this is 596. Okay. So, and so on. So, so I will leave you to check why this is the right answer. Okay. But nevertheless, so yeah, you can also check from the previous code that yeah, this number was 596, right. So, are just going to replace x of I, not every I, it is actually m plus I. Okay. So, since it is m plus I minus m is just I. So, I will write it as 5 power I plus 1 minus 2 power I plus 2 plus 3. Okay. So, instead of m, so if you substitute from 0 to m minus 1, right. So, I can substitute I as m plus I, right. So, yeah, I mean I can rewrite this as x of m plus I equals 5 power I plus 1 minus 2 power I plus 2 plus 3 for all I in 0 to m minus 1, right. So, I have just changed the way I write I, right. So, yeah. So, that is what I have written down here, 5 power I plus 1 minus 2 power I plus 2 plus 3, right. And now we will write A. So, I have written down C and X in general for all values of m, right. But for A, yeah, we have to struggle to some extent, right. So, the m plus 1th row we will write it later, because we just have to replace one entry by 1. Okay. We will concentrate in the other entries, right. So, we will first put this diagonal as 1 and this diagonal as 1. Okay. So, that will be A of I comma I is 1 and A of I comma I plus m is also 1. Okay. So, those two diagonals are done. Okay. We will also finish this, right. So, that is minus 5 power I plus 1. So, that is A of I comma 2 into m, right. So, if you start with 0, that is column number 2m, right. So, that is just minus 1 into 5 power I plus 1, right. Now, we still have to fill these diagonals. So, recall that so this diagonal is 1, that is okay. The diagonal just below the diagonal of 1s you have 4s, below that you have 8, below that you have 16, below that you have 32 and so on. Okay. So, we will do the general filling now. Okay. So, this will be another loop. Okay. So, if it is okay, we will start actually from so it is just up to m minus I. Okay. So, if it is 0, we have filled the 0th column here. So, since it is the first column, okay, we are starting from row 0 and row is 1, but the column is 0. Okay. Okay. So, this has to be, yeah, the column number has to be j. Okay. and this is, yeah, so what we have to fill is 2 power j plus 1, right. Yeah, so we will start from 1, okay, and then go up to m minus I, okay. So this will be I plus j comma I, and this is 2 power j plus 1, okay, 2 power, sorry, yeah. To explain what is happening, okay, so note that when I is equal to 0, okay, and note that we are starting j from 1, okay. So the first entry will be a of 1 comma 0 equal to 4, okay. So that is what we have here, a of 1. So this is 0th row and 0th column, okay. So the first row and 0th column has 4. So a of 1 comma 0 has 4, okay, and this one is 2 comma 1, okay. So when you put I equal to 1, that is in the next cycle, right. So you will have a of 2 comma 1, but this will be 4 because j is equal to 1 again, right. So and similarly 3 comma 2, 4 comma 3, everything will be 4, okay. If you are looking for 8, so here you will see that a of so it starts with I equal to 2, I mean when sorry j equal to 2, right. So yeah, when I is equal to 0, it is a of 2 comma 0, which is 8, 2 power 3, right, and the next one will be a of 3 comma 1, which is again 8, and so on, okay. So yeah, we have filled C, X and A, okay, and yeah, so this C and X can be removed, okay. Yes, we have not written down the final row of A, so that is one thing that we have to write as well. So last row where you have all zeros and a 1, right. So that has to be filled up with A of so that is m plus 1 comma 2 into m, sorry m comma 2 into m, that is actually 1, okay. So that is just one entry that we need to change. Little a is the last row, n is the shape of 0, okay. So that is the reason I started with m, okay, because n we are using for something else. 2m plus 1 basically, that is n. Capital X is diag of x, k equal to 0, and yeah, so we have the mu and the rest of the algorithm, okay. So let us check if this algorithm work for m equal to 3, okay. Double parenthesis, okay, yes. So we have the answer. So yeah, the answer is 0, 0, 125, 5, 25, 0 and 1, okay. So that is something we know already, right. So good, yeah. So we have got that in 214 iterations, right. So let us note that down, okay. This is Karmaker's algorithm, right. Yeah, let us write down a table. So for the value of m, okay, what is the number of steps that Karmaker's method takes, and what are the number of steps that the simplex method takes, okay. So for m equal to 3, we know that simplex takes 2 power 3, 8, isn't it. So but Karmaker's has taken 214 iterations, right. So okay, that is much more than 8, that much of math we know, but I mean we were told that Karmaker's method performs much better than simplex algorithm, right. So okay, maybe it did not work for m equal to 3, let us try for slightly higher values of m, okay. So let us actually first start with m equal to 5, okay, which is slightly higher, right. Okay. So let us see how many iterations Karmaker's method takes. Okay, it has taken 600 iterations, yes, but the answer is 0, 0, 0, 0, 3125, 5, 25, 125, 625, 0 and 1, okay, good. For 5, it has taken 600 iterations, and this we know that it is 32, 2 power 5, right, okay. So still simplex is performing better, right, okay. So let us do it for a slightly higher value, say 10, okay. For m equal to 10, let us see how many iterations does our Karmaker's algorithm take, okay. Okay. So it has taken 4262 iterations, okay. So again you can see that the first 4 are 0, the next 4 are 0, this is 0 and this is something very high, right. Yeah, that is expected, it is about 5 power 10, right. So that is expected to be very high, right, okay. But it has taken 4262 iterations, okay. But simplex algorithm will take 2 power 10, which is 1024. Okay. So, still simplex is performing better, okay. But one thing that you should have noted is that the number of steps Karmaker's algorithm took in 5 in comparison with simplex was much higher, right. So, this is roughly 4 times of simplex when you put m equal to 10, right. Okay. So, that is understandable. So, let us try some higher values as well, okay. Maybe m equal to 12 to see how many iterations does Karmaker's method take. Okay. It has taken roughly 7488 for 12, okay. And this would have taken 4096, is not it. So, 2 power 12 is 4096, okay. Let us possibly stop with 15, okay. So, let us check how many iterations does Karmaker's algorithm take, okay. So, we will do it for m equal to 14, the final one that we will attempt now, okay. So, fine, yeah, we will try with m equal to 14 and check how many iterations does Karmaker's method take. Yeah, it takes 11,588, right. And what is 2 power 14? Yeah, if you have computed already, you would have got 16,384, okay. So, at least there is some value of m for which Karmaker's algorithm takes a lesser number of iterations than the simplex algorithm, okay. But this is not surprising, okay, because when we say 2 power n, right, 2 power n seems to be a very less number when your value sorry 2 power m rather. So, since we have m used m here, right. So, 2 power m seems to be like a very small number when you actually consider low values of m, right. So, for example, take m equal to 3. So, 2 power 3 is just 8, 8 is a very trivial number, right. So, if simplex algorithm is just taking 8 iterations is very low, right. So, why did we really worry about saying oh 2 power m, okay, maybe 2 power m is not large, right. 2 power m is not large if m is small, right, but it shoots up really very badly when m is large, right. So, yeah, I am not sure how many students would have heard of the P class and NP class in the theory of complexity, right. So, when we discuss about complexity of algorithms, okay. So, we say certain algorithms as polynomial time algorithms, which is P, okay, and NP is actually non-deterministic polynomial, okay. So, I mean I would not like to elaborate on this since it is beyond the scope of this course, okay. But I will just give you an idea of what this polynomial time and those algorithms which do not follow this so called polynomial time algorithms, okay. So, yeah, 2 power n is certainly not polynomial, right. So, that much you know, okay. And Karmaker's algorithm, okay, so is said to have yeah, it follows a time complexity of so this time complexity of Karmaker's method, right, in the worst case is given to be O of m power 1.5 n squared into L, okay, where m is number of constraints, n is number of variables, and L is number of bits as input. Okay. So, yeah, in this case the number of constraints is 2m, right. The number of constraints is m plus 1 and the number of variables is 2m plus 1, right. So, I mean let us do a comparison of this Karmaker's methods m power 1.5 n squared and simplex method, okay. So, suppose it takes, I mean, so 1 second to compute the answer in simplex method. When m equal to 14, sorry. Okay. So, yeah, that means 2 power 14 iterations take 1 second, right. So, 2 power 15 iterations will take 2 seconds, 2 power 16 will take 4 seconds, all that is fine. How many iterations will 2 power 28, sorry, how many seconds will 2 power 28 iterations take, right. It will actually take 2 power 14 seconds, right. 2 power 14 is, yeah, we just wrote it here, right, 16,384 seconds. Okay. So, 1 hour is 3,600, right. So, this is, I mean, yeah, slightly less, but about 4.5 hours. Okay. So, when m is equal to 14, okay, we assume that it completes in 1 second. Okay. Yeah, computer is fast, it computes in 1 second. Okay. But suppose you give m equal to 28, simplex algorithm to converge to the answer, it takes 4.5 hours. Okay. So, it is so slow, right. I mean, you can see that yourself, right. I do not have to explain that anymore. Okay. But this is about simplex algorithm. Now, suppose take Karmaker's algorithm in this case. Okay. In Karmaker's algorithm, yeah, so of course, the number of iterations is less, but let us say there also it takes 1 second. Okay. Maybe it is slightly less than 1 second, but let us say it takes 1 second. Okay. So, yeah, in Karmaker's algorithm, okay. So, let us assume that for m equal to 14 it takes 1 second. Okay. Now, what happens to m equal to 28? So, this was O of m power, so m is number of constraints, so that is 15 power, right. So, it is 15 power 1.5 and n was 2m plus 1, which is 29, 29 squared into L. Okay. So, for 28 it will be O of 29 power 1.5 and 57 squared L, right. So, yeah, 29 by 15 is roughly 2, yeah, it is slightly less, but it is okay, I will write it as approximately. So, it is 2 power 1.5 and here also it is roughly 2. So, it is 2 power 3.5 O of 15 power 1.5 29 squared into L. Okay. So, what is 2 power 3.5? 2 power 3.5 is 8 into square root of 2, right. So, that is, yeah, 1.4 is about 11.2 is what I am getting. Okay. So, yeah, maybe I will write just write S, I think it is fine. Okay. So, what this tells us is that when you use Karmaker's algorithm for large values of m, okay. So, yeah, whatever we work out in class is like some small problems, right. So, when you work out large problems like what we had worked out in this example, right. So, Karmaker's algorithm performs much faster than simplex algorithm. So, we just saw this in simplex algorithm, it for when m equal to 28 it is taking 4.5 hours, whereas in Karmaker's algorithm it just takes 11.2 seconds, right. So, when m is large, you can see that Karmaker's algorithm performs much better than the simplex algorithm that we see here, right. So, that is the reason, I mean, people use Karmaker's algorithm when at least for cases when the problems are large, right. Of course, simplex method is still in use because small problems, I mean, we can still find an exact answer when you use simplex method. Okay. But I suppose I mean Karmaker's algorithm gives a better algorithm in terms of speed when you have large problems. Okay. So, we will end our discussion on linear program with this. So, recall that we have discussed about simplex method, affine scaling and Karmaker's algorithm. Okay. In the next week, we will discuss about an application. Okay. So, we have discussed so many algorithms now. So, I will explain some application and then discuss in detail how you apply these algorithms in that application in the last week of this course. Thank you.